Hello everyone. Good morning. Good morning. Okay. Okay. Can you hear me? 잘 들려요? Okay. So I'd like to start today's lecture. Are you ready? Okay, good. Okay, so in last time we have talked about the reaction in ligand by using transfer method. So I want to review the last time. So we have talked about associative substitution and dissociative displacement. And then we also look at the effect of the cone angle. So if a cone angle is bigger, getting bigger, the rate constant is fast. It means that bigger cone angle ligand can easily removed from the transfer metal because cone angle generate steric hindrance. And we also talk about CC effect and interchange pathway. And then we have talked about oxidative addition. So we have learned that oxidative addition is reversible reaction. So oxidative addition and reductive elimination. So both reactions are very important to explain some transition metal catalysis. 그러니까 I want to say in Korean. 그러니까 여러분들 다른 건 다 기억이 안 나도 괜찮은데 옥시데이티브 어디션과 리덕티브 엘리미네이션은 금속 촉매를 이용한 반응에 정말 필수적인 두 가지 요소예요. 그러니까 꼭 기억하세요. Oxidative addition, reductive elimination. So in case of oxidative addition generate the metal inserted between XY bond. So during this reaction, the oxidation state is increased. So we call oxidative and added between some bond. So we call oxidative addition. The reverse concept is reductive elimination. So during reductive elimination, the oxidation state is decreased and elimination occurred. So we call reductive elimination. So now we are talking about oxidative addition. The first case is non-polar bond. In organic chemistry, HH bond or CH bond or CC bond. In organic chemistry, these bonds are non-polar. Although there are some difference of electronegativity. However, in organic chemistry, generally we say these are neutral and non-polar bond. So rhodium can be added between proton-proton, or iridium can be added between proton-proton, something like that. So in this case, the mechanism is like this: 3-center concerted addition. So 2 hydrogen and iridium make 3-centered triangle. So if there is a so this is hydrogen gas and this is transition metal. If transition metal is come to the hydrogen gas, so it generates like this: 3-centered transition state, and then concertedly, 동시에 concertedly hydrogen added to make this like this. So we call 3-center concerted addition. So because HH, CH, CC non-polar bond generally 3-center concerted mechanism. So CH bond activation, all the 3-center concerted mechanism because these are CH bond and CH bond. So sometimes the addition of CH bond we call CH bond activation, because generally CH bond, we know that CH bond is not reactive, just less reactive, but we try to use that, so we call CH bond activation. Okay, how about addition of X2? So now different type of oxidative addition. So we are talking about HH, HC, CC, but now X2. X2 means halide, such as bromide, Br2, or Cl2. X means Br2 or Cl2. So, as you know, Br2 and Cl2, the bond is non-polar. However, Br and Cl both are electron rich. Electron negativity is high. So if you think about the addition between double bond, if you think about the reaction between olefin and double bond, olefin will attack the Br to generate bromonium. This is the first step between the addition of Br2 of double bond. Similarly, double bond are electron rich. Similarly, transition metals are electron rich. So, the first step is transition metal will attack the brom, and one bromide is kicked out. Similar to alkene addition, transition metal attack the transition metal attack the bromide and kick out the one bromide. So release the bromide X minus, and the generated X minus attack the organometallic compound and then kick out the one ligand. During this step, we have learned that associative or dissociative, maybe dissociative mechanism, because it has the coordination number is 6, so maybe the dissociative mechanism will be plausible. Anyway, quite similar between olefin and bromination. So transition metal attacked the bromide and bromine kicked out, and then 6 coordination transition metal complex, and then carbon monoxide is kicked out and bromide come through to make the final product. So if we look at this compound, it looks like transition metal is inserted between the XX bond. So, but the mechanism is not 3-center concerted mechanism. The mechanism is step by step, so not concerted. How about RX? RX means carbon halide bond. Carbon halide bond. So if R is methyl halide, because methyl is very small, so transition metal complex can behave as nucleophile. So similar to SN2. So transition metal will attack the carbon, kick out the iodide, and then the released iodide will be added to transition metal again to make the complex. So, as you know, this is step-by-step reaction, so not concerted mechanism. Okay, so let's look at the whole reaction. So if you think about the first step, so palladium will attack this carbon and kick out the halide, and then the generated halide again attack the palladium to generate this complex. So as I told you, it looks like SN2 reaction. So this carbon will be inverted. And then carbon monoxide will be inserted, in this case retention, and methanol will attack this carbon and going up, going down, kick out the palladium. So to make this one. So what I want to say in this slide is depend on the mode, depend on the method, or depend on the mechanism of the oxidative addition, the configuration, stereocenter will be inverted or retented. So the mechanism is very important to predict the stereocenter. Okay? Okay, so final oxidative addition, we need to talk about radical pathway. So some reagent such as halide, alkyl halide, but R is not methyl in this case. So if R is methyl, we suggest that similar mechanism SN2 So in case of R is methyl, the reaction mechanism is similar to SN2 reaction. However, in this case, R is not methyl. For example, phenyl or benzyl, something like that. In this case, radical pathway would be fast. Because if you think about benzyl halide, if you think about benzyl halide, as you know, the radical in toluene is very stable. So in this case, in case of benzyl halide, the benzylic radical will be generated easily because of the transition metal. So in this case, radical mechanism. Okay, I want to summarize the oxidative addition pathway. In case of non-polar bond such as HH, CH, or CC, the mechanism is three-centered consultative mechanism. Aryl halide or vinyl halide include, in this case, three-centered consultative mechanism. So generally retention of configuration, and because three-centered insertion, two new ligand should be cis position. However, in case of polar XX halide, the transition metal attacked the first halide and first halide kicked out, and kicked out halide is come to the new ligand. So in this case, stereochemistry is not available. However, generally trans would be generated. How about SN2-like? In case of methyl halide or allylic halide, benzylic halide, we know that these primary alkyl halide is good electrophile in SN2 reaction. So if the alkyl halide is good electrophile in SN2 reaction, in transition metal catalysis, the oxidative addition is take place like SN2-like mechanism. So in this case, the number of step is 2 step, and generally inversion of configuration would be generated. And then stereochemistry is usually trans. How about radical mechanism? If R is not aryl or vinyl or methyl, allyl, benzyl, in this case, radical mechanism would be favored. However, if you think about the benzylic, this alkyl halide is good for SN2 or radical, so depend on the reaction condition. So SN2 mechanism or radical mechanism would be generated. So the basic concept is the mechanism of oxidative addition is quite similar to the SN2 reaction or three-center consultative mechanism. Okay, do you have any question about oxidative addition? If not, we will talk about reductive elimination. Okay, reductive elimination, we generally say RE, is reverse of oxidative addition. So you just think about the reverse reaction. Okay, so I want to generate reductive elimination of this part. this part and this part. What happened? What happened? So in this case, three-center concerted mechanism, like three-center concerted mechanism, like three-center cyclic triangle is generated, and then breaking this bone and this bone, and this bond is strongly attached to generate this one. So sometimes some nucleophile attack the carbon and palladium is generated. It can considered as reductive elimination, but not general. Not general. So this first example is general reductive elimination. So reductive elimination is during reductive elimination, the oxidation state is reduced +2 to 0 or +4 to +2. So generally, high oxidation state transition metal complex like reductive elimination, because high oxidation state is too high, so they try to reduce the oxidation state. So this pathway is good for CC bond formation. Okay, CC elimination. The first mechanism is CC elimination. CC elimination is reverse of three-center oxidative addition. So like this and this and this. So exactly reverse of three-center oxidative addition. Okay. How about this? So palladium is here, and methyl is here, and phenyl is here. So three centers, and then reductive elimination to generate this one. Okay, evidence. How about this evidence? So if you have this complex, and if you take reductive elimination, in this case, this butane is generated. It means that this is generate new compound. So reductive elimination. How about this? Ethyl, ethyl. So now the ethyl is trans to ethyl. So in this case, if you carry out the reductive elimination, the reductive elimination is not take place. So you cannot obtain butane in this reaction in case of trans. So this is the evidence of cis elimination. In case of trans position, instead of reductive elimination, beta hydride elimination is take place. What is beta hydride elimination? If you think about this complex, I want to draw this complex in ChemDraw. Palladium is here, Uganda is here, Uganda is here, ethyl is here. So now this structure is this. I draw the ethyl like this, just to express one important hydride. So palladium will cleave this bond. So palladium electron push is here and here. So to generate this complex. So this complex is reductive elimination. But if you think about reductive elimination, the paradigm already used 4 coordination. So the one empty coordination should be the top. So this is my hand is palladium, ligand 1, ligand 2, ethyl. So ethyl 이렇게 write this, and this is proton. So in this case, this proton should be going top to generate reductive elimination. If proton is going top, the proton and ethyl should be cis position. So this is the beta hydride elimination to generate ethene, and then so now the ethyl and hydride is in cis position. So finally, reductive elimination can be take place in this stage. So ethane is generated, not butane. So this is the evidence why cis elimination is favored. How cis elimination occurs in transmetal complex. 그러니까 여러분들 중요한 건데, I want to say in Korean because this is very important concept. 그러니까 지금 cis elimination의 그런 메커니즘을 지금 설명하고 있잖아요. 여러분들 뭐 이거는 그렇게 어려운 게 아니니까. cis elimination은 이 cis 위치에 있을 때 마치 그 3center concentrated 메커니즘의 반대 방향으로 반응이 일어나는 거예요. 그러면 에비던스가 뭐냐? 에틸이 두 개가 시스에 있을 때는 뷰텐이 만들어져. 근데 에틸이 트랜스로 있을 때는 뷰텐이 안 만들어져. 왜 안 만들어지고? 그럼 뭐가 만들어지냐? 이 에틸이 이렇게 돼 있는데 이 에틸의 베타 하이드라이드 엘리미네이션이 먼저 일어납니다. 그러면 팔라듐이 이렇게 있고 에틸이 이렇게 있을 때 에틸의 H는 반드시 위로 들어가야만 팔라듐의 MT 코디네이션 사이트를 들어가는 거야. 위로 들어가면서 수소를 주고 에틴이 이 이중결합이 떨어졌어. 그러면 내 엄지손가락이 에틸, 리간드 이쪽에 있는 건 떨어졌고 H가 위에 있으니까 이 위에 있던 게 어떻게 해요? 뭐 이쪽으로 갈 수도 있고 이쪽으로 갈 수도 있고 짜부가 되면은 결국은 트랜스 위치로 있다는 거지. 트랜스 위치. 이게 일로 가지는 않지. 왜냐면 이 상태에서 테트라이드로 구조로 다시 펴질 거니까. 그러면 위에 들어가서 다시 에틸과 H가 시스가 있으니까 그때 이제 그게 되는 거죠. 리덕티브 엘리미네이션이 일어나서 최종 생성물을 만든다라는 겁니다. Okay, so I'm sorry. We are talking about the reductive elimination. So you need to and then we are talking about cis elimination. So to make reductive elimination, the ligand should be in position in cis position. Okay, so in this case, reductive elimination can be done, but in this case, cannot. In this case, possible is not possible. It's possible, it's not possible. Like this. Okay, complex 31 shows no reductive elimination, but with CD3I, ethane is produced. So this is not possible reductive elimination, but if you add CD3I, the ethane is produced. Probably the CD3I generate cis position of methyl methyl group. How? So I'm sorry. So in this case, if you add a solvent will add it to the palladium. So reductive elimination is faster. How about this? In this case, trans. So we know that trans is reductive elimination of trans is not possible. But if you add a solvent occupy the top and generate new type of complex, and then generate new type, and then solvent kick out, so cis position is produced. So in transition metal catalysis, the choice of solvent is very important. So you need to be careful to choose the solvent. Okay, let's look at the complex 31. So if you add something, the addition to transition metal, and can then the ethane can be generated. So this is the indirect evidence. If you add CD3 complex and CH3 complex, only CD3 ethane, CH3 ethane is generated. It means this result means that only intramolecular reductive elimination possible. No crossover. Crossover means exchange the ligand each other, but no crossover. Okay. So if you think about reductive elimination of this compound should undergo the cis generation and then reductive elimination. How about stereochemistry? So as I told you, transition metal can attack the carbon and kick out the bromide, and bromide attack the transition metal. So inversion is generated in oxidative addition. But reductive elimination, only retention. So reverse configuration is generated. How about cis bond elimination? Okay, so if you look at the transition metal undergo oxidative addition and ligand kicked out and reductive elimination takes place. Okay, this is cis isomerization. So if you think about the three-center reductive elimination, so first three-center reductive elimination takes place and kicked out. So and then oxidative addition again. So isomerization can be produced. Okay, so this is the all over the organic chemistry organometallic reaction 1. So we can take a break for a while, and then we will talk about organochemistry reaction 2. So in this chapter, we will talk about the important story, important part. Okay, we will take a rest for a while, and then 10 now is 10:40. Okay, 10:55. Okay. 네. Okay, see you later.